Welcome to FPGA episode 34. In this episode, we're going to be implementing 3D rendering in real time. We'll take a couple of cubes, paint them with different colors, throw them into space, and have them rotate on a circular trajectory with a speed that's constant without user intervention, or can be sped up or down using the left and right buttons on the pink Z1 board. The design leverages both the PS to handle the software part of the application, which computes the changes in the 3D positions of these cubes on every frame, and decompose this information into a network of triangular polygons that the PL fabric can then take as inputs and in turn generate the rasterization of the pixels. We'll cover the Zinc interface block first, as it highlights the overall architecture between software and hardware. This should look somewhat familiar by now to most of you. What's most important in this picture is the DMA channel allocated to move 3D polygon data from the PS side to the PL fabric. This bus is 32-bit wide and is set to run at 200 MHz in this design. There is an interrupt line allowing the PS to be interrupted in a timely fashion on every frame to update changes for the 3D scene and set up the DMA for this updated info to be sent to the PL side. We're now looking at the main software application of the project. We have a couple of driver instances and declarations that we were discussing earlier, looking at the Zinc interface block diagram. We have an interrupt handler in this application that is triggered once every frame. The resolution of the display has not changed and is still 1280 by 720 pixels. These next parameters control the scene viewing. The slopes of the triangular polygons when rasterized have a fractional fixed point resolution of 16 bits. We'll cover the two functions, triangle rotation and flat edge after, when we get to their actual definitions at the end. The design in this project demonstrates support for 64 triangular polygons or 128 flat-edge triangles, as each triangular polygon can be decomposed into a pair of flat-bottom and flat-top triangles. Each pair requires 16 32-bit words for configuration, and a total of 256 times 5 words are needed as buffer to support the system DMA. Notice the alignment on 256 words, as that is the burst size of our DMA channel. The cubes have an initial X rotation of -25 degrees and Y rotation of 35 degrees. Following that, absolute rotation and actual positions on the screen are controlled by dynamic parameters that get updated as the cubes start to rotate. The main function starts with setting up all the drivers and initializations. Each cube has a unique color. The DMA buffer is initialized to zeros and filled with the initial first scene. DMA is then kicked off to update the PL fabric with this information. Frame interrupt is also enabled. At every frame interrupt is disabled, and the software updates the rotation speed accordingly. It then calls the triangle rotation function to update the positions of all the cubes, or in another word, the actual triangular polygons on the faces of each cube. The DMA is again kicked off to transfer this updated info to the PL fabric for the rasterization of pixels to take place. Interrupt gets turned back on. Let's now walk through the triangle rotation function to uncover the implementation. For each triangular polygon, the 3 sets of XYZ coordinates go through a 3-axis rotation update. The updated coordinates then get mapped to the screen's 2D X and Y. It also attempts to vary the color intensity of the plane based on where it is with respect to the viewer to encode some depth. The next task is to figure out the actual shape of this triangle to properly decompose it further into a flat bottom and a flat top triangle. After proper decomposition, it then gets the actual flat edge function to update scene parameters with the information needed by the PL fabric to do the rasterization. That is it for the main software application. Let's now move on to the PL fabric. We have already covered the Zinc interface block diagram earlier, so we can just start with the top-level RTL. I/O at the top level is very similar to what we've seen in past episodes. We have the 125 MHz clock input, the Zinc DDR and I/O interface. We have that HDMI TMDS interface, and the right and left push buttons to change the rotation speed of the cubes if desired. Next up, you can see that parameters related to the number of triangular polygon pairs, the number of 32-bit words needed for each pair, and the total DMA length match up with what we defined on the application software side. Each flat bottom and flat top triangle need its own set of screen coordinates, slopes, and color. The design is implemented with support for a fixed number of polygons, and it's up to the application software to use however many. Here we track the DMA operation and synchronize the input buttons. As DMA data comes in, we offload them to the correct destinations for each pair of triangular polygons. This process repeats every frame. We have an army of pairs of flat top and flat bottom triangles, and this is where they all get created. As you notice, for each flat top and flat bottom triangle, we also have two different versions. One version uses available DSP resources to handle the math, and one version does not. This design attempts to leverage most of the available DSP resources of the FPGA to handle the math, and the rest with regular logic elements. Next up is combining all the pixels from all the rasterization modules. Followed is the usual HDMI TMDS interface and the Zinc instantiation. That is it. Let's program the board and see our flying cubes in action one more time. The design files are on GitHub. Link is in the video description. Have fun and see you warriors in the next episode.